Okay, hi Chris. Hi Chris. So let's look over what you missed last week and this week. So on Friday, we talked about what are called matrix solutions to linear systems. So to get started, a matrix is a rectangular array of numbers. The numbers within a matrix are called the elements of the matrix. Matrices are used to display information and to solve systems of linear equations. Because systems involving two equations and two variables can easily be solved by substitution or addition, we'll focus on matrix solutions to systems of linear equations in three or more variables. A matrix gives us a shortened way of writing a system of equations. The first step to solving a system of linear equations using matrices is to write the augmented matrix. An augmented matrix has a vertical bar separating the columns of the matrix into two groups. The coefficients of each variable are placed to the left of the vertical line, and the constants are placed to the right. So for example, to write the augmented matrix for this system, so we're going to sort of create a box of numbers here. In the first column we have the x numbers. So in the first equation we see a 1x, in the second equation we see a 2x, in the third equation we see no x's. Then we go to the next column will be the y's. I see a negative 2y in the first equation, a 3y in the second equation, and a 1y in the third. Finally, in the z column, in the first equation I see no z's, in the second equation a 1z, and in the third equation a negative 4z. I'll separate the left and right hand sides of the equations with a vertical bar and then write the numbers on the right side. So that's 2, 11, and negative 7. So this is called the augmented matrix for this system of equations. Now, let's talk about what is it we're going for here. Our goal in solving a system of linear equations in three variables using matrices is to produce a matrix with ones down the diagonal from upper left to lower right on the left side of the vertical bar, called the main diagonal, and zeros below the ones. So it's going to look like this. I have ones along the diagonal, I have zeros below the diagonal, and then the rest are just whatever numbers they are. So the third row of this matrix gives us the value of one variable. Like this equation now says 1z equals f. In other words, z equals f, whatever number that may be. Then we can back substitute. If we know the value of z, I can go into this equation that says 1y plus something z equals a number. We know the value of z, so we can just solve for y. Y is easy to solve for here because it's a 1y. In the first row, we have a 1x. So we'll plug in the known values of y and z, and then we can easily solve for x. So on the next page we're going to go over the matrix row operation. So there's three operations we do with matrices that help us solve a system, and really these correspond to the types of things we would do in a system of equations that we would solve by like the addition method. The one that might be new is that two rows of a matrix may be interchanged. Really, that's like if you have a system of equations like these three up here. Whoops, sorry, I missed that. If I have a system of equations like these three up here, it doesn't matter what order I write them in. This first equation could be switched with this second equation, like they could switch places. As long as all three equations are there, it doesn't matter what order they're in. So this first thing where it says two rows of a matrix may be interchanged, that's what it means. We're just switching the order of the rows. And why would we do that? Well, we'd like to have a 1 in the top left place. So if there's not already a 1x in the top equation, we can just switch it with an equation that does have a 1x, and then we have a 1 in the top left place. The elements in any row may be multiplied by a non-zero number, just like an equation, which represents a row, can be multiplied by a number. Like up here, I could multiply 2x plus 3y plus z equals 11 by 2 on both sides, and it would be the same equation. The third row operation is that we can multiply a row by a number and then add it to another row. For example, if we think of equation 1 as like the first row and equation 2 as the second row, If I were wanting to eliminate the x's, I could multiply row 1, if we want to call it this, by negative 2 and add it to row 2. Then we'd have a negative 2x and a positive 2x, and they would add to 0. Okay, so the sort of notation to do this, to interchange two rows, we write a double arrow between those two rows, whatever row numbers they are. To multiply a row by a number, we write that number in front of the row with its corresponding number. To add some number times row I to row j, we do this, k times row I plus row j, whatever those numbers may be. To see a specific example, in example 2, we use this matrix to do parts A, B, and C. So in part A, this means interchange rows 1 and 2. So I'm going to interchange rows 1 and 2. Okay, so like we see 4, 12, negative 20, and 8 is the first row. Now it's the second row. We see that 1, 6, negative 3, and 7 is the second row. Now it's the first row. The third row, well, we're going to keep it the same as it was before. We're only interchanging the first and second. So that's our new matrix. In B, so this says 1/4 times row 1. So in other words, I'm going to multiply row 1 by 1/4. Okay. Well, let's see. If I multiply 4 by 1/4, that's 1. If I multiply 12 by 1/4, that's 3. If I multiply negative 20 by 1/4, that's negative 5. If I multiply 8 by 1/4, that's 2. The second and third rows are the same as before. 1, 6, negative 3, 7. Negative 3, negative 2, 1, negative 9. So our new matrix is has the first row multiplied by 1/4 of what those numbers were in the original part of the example. In C, we see 3 row 2 plus row 3. In other words, multiply row 2 by 3, add the result to row 3. Now, one thing that's not said but is happening in the background is that this is the new row 3. So when we write 3 row 2 plus row 3, the implication is that this will replace row 3. So first let's carry out the calculation. So I'm going to write 3 in front of row 2. So 1, 6, negative 3, 7. So there's 3 times row 2 plus row 3. So negative 3, negative 2, 1, negative 9. And now let's do the addition. 3 times 1 is 3, minus 3 is 0. 3 times 6 is 18, minus 2 is 16. 3 times negative 3 is negative 9, plus 1 is negative 8. 3 times 7 is 21, minus 9 is 12. So this thing is going to be the new row 3. First and second rows, unaffected. So I've got, as usual, 1, 3, negative 5, 2 as the first row, just like in the original. Oh, I apologize. That was after I multiplied by 1/4. 4, 12, negative 20, and 8, just as in the original. Row 2 is still 1, 6, 3, 1, 6, negative 3, 7. the new row 3 has these entries. So 0, 16, negative 8, 12. See, what we did here, if we think about the system of equations, this is a 1x and a negative 3x. So we multiplied this equation by 3 to get a 3x, and then 3x and minus 3x make 0x, so we eliminated x. That's what's happening if it were a system of equations. Okay, so then to solve a system of equations using, this is called Gaussian elimination, the process we're going to illustrate in the next two examples. We write the augmented matrix for the system, in other words, writing something like this. We use the row operations we did in example 2, interchanging rows, multiplying rows by numbers, adding rows together, to simplify the matrix into what we call row echelon form. In other words, row echelon form looks like this, where you have ones down to the diagonal and zeros below the diagonal. And then we write the solution that we get in row 3, because this says z equals some number, and then we start back substituting into the other rows. So let's see some specific examples. Okay, so in the third example, so we're going to solve a system of equations. So I see a 2x, a 1x, and a 1x. So my first column will say 2, 1, 1. Next, a 1y, a negative 1y, and a 2y. Finally, in the z column, 2z, 2z, negative 1z. So I'll write 2, 2, negative 1 in the z column. On the right side, 18, 9, and 6. The idea here is I would like the first column to say 1, 0, 0. I don't have a 1 in the top left place right now, but I can make a 1 by just switching the first two rows. So let's interchange rows 1 and 2. So my next matrix, so I've interchanged rows 1 and 2. So instead of the first column saying 2, 1, it's going to say 1, 2. Instead of saying 1, negative 1, it's going to say negative 1, 1. The 2's changing doesn't do anything. Instead of 18 and 9, we see 9 and 18. So we have our 1 in the right place. Now we'd like to get zeros below it. So if we imagine that this is like a 1x and this is a 2x, well, maybe we would run a negative 2 through that top equation and add it to the second equation. Because what would this do? This would make a negative 2x plus 2x, making 0. And so that's going to replace the second row. I'm going to write the new equation I would get in the second row that has no x's. In the first and third equation, because I'd like to make this a 0, well, I have a 1x here and a 1x here. So if I ran a negative through this equation, so negative row 1, and added it to row 3, I'd have negative 1x plus 1x. That would make 0x. I'm going to write that new equation that I get by eliminating x in the third row. Now, the first row is being used to change the ones below it. I'm not going to actually change that row. So I'm just going to rewrite row 1. Not only that, but I know by design, by the way I did this calculation, the 2 and the 1 are going to become zeros. Negative 2 times 1 is negative 2, plus 2 is 0. That was the whole point of doing those calculations. That's why I did negative 2 of row 1 plus row 2, and negative row 1 plus row 3. But the question is, what happens to the coefficients of everything else? So let's go through the second row and see what the new numbers are. So if I go to the y column, so I'm doing negative 2 of row 1 plus row 2. Negative 2 times negative 1 is 2, plus 1 is 3. In other words, I have a 3y in this new equation. Negative 2 times 2 is negative 4. Negative 4 plus 2 is negative 2. So I have a negative 2z in this new equation. On the right side, negative 2 times 9 is negative 18, plus 18 is 0. In other words, I've created a new equation, 3y minus 2z equals 0. Next, for the third equation, or the third row I should say, so to create the new third row, I'm doing negative row 1 plus row 3. Let's see what that means for y, z, and the right side. In the y column, negative 1 is 1, plus 2 is 3. In the z column, negative 2 minus 1 is negative 3. On the right side, negative 9 plus 6 is negative 3. So what I've done here in this to create this matrix, I've eliminated x twice using equations 1 and 2 and using equations 1 and 3. By eliminating x, I've created two new equations, 3y minus 2z equals 0, 3y minus 3z equals negative 3. Now x has been eliminated. Next I want to eliminate y in equation 3. So we get a 1, 0, 0 for the first column. I would like a 1, 0 in the second column. Now this says 3y. I can turn it into a 1y by just dividing it by 3. So what I'm going to do to create a 1 is I'm going to run a 1/3 through row 2. So that's the easy way to create 1. You just divide a number by itself. The first and third rows are not mentioned in this calculation, so I'm just going to copy them from the last matrix. So 1, negative 1, 2, 9 is still there. The third row is also not part of it, so 0, 3, negative 3, negative 3. In the second row, a third of 0 is still 0. A third of 3 is 1. A third of negative 2 is negative 2/3. A third of 0 is 0. So now I have a 1y. That's going to be now easy to solve for y when I finish solving this system. But I would like this 3y below it to be a 0y. I'd like no y's in equation 3. Well, if I have a 1y here and a 3y here, then what I could do is say, let's take negative 3 of that second equation and add it to the third equation. Then I'd have a negative 3y plus a 3y, and that would be 0. So that's going to become the new third row. First row is not part of this, so I'm just going to rewrite it. The second row is only being used to change the third row. So I'm just going to rewrite the second row as well. So the third row is what's changing. This is going to give me an equation that only has z in it. So let's go piece by piece and do this. Now, the first column, I already got my 1, 0, 0. Once you do that, it's not going to change. Next, the whole point of doing negative 3 row 2 plus row 3 was to make this a 0. So there's no mystery that that's a 0. So it's really just down to finding what's the new coefficient of z and what's on the right side. Negative 3 times negative 2/3 is 2. 2 minus 3 is negative 1. On the right side, negative 3 times 0 is 0. Minus 3 is negative 3. In other words, by using the addition method, I've eliminated y in the second two equations and given myself an equation that has only z. And it's easy to solve for z. This says negative z equals negative 3. So we would multiply or divide both sides of equation 3 by a negative 1. Equations 1 and 2 don't change, so I'll just rewrite them. 1, negative 1, 2, 9. The second equation doesn't change. 0, 1, negative 2/3, 0. On the right side, on the third row, all I'm doing here is just multiplying all the numbers by negative 1. That's not going to mess with the zeros. It turns negative 1 into positive 1 and turns negative 3 into positive 3. This matrix is now in the sort of the proper form. We call it row echelon form, but it's in the proper form to finish. We have 1s down the diagonal and 0s below those 1s. Now, the third row says 1z equals 3. Now I'm going to back substitute that into the second row. So the second row says y minus 2/3 z equals 0. Well, we happen to know that z is 3, so that's y minus 2/3 times 3 equals 0. 2/3 times 3 is just 2, so I have y minus 2 equals 0. Therefore, y equals 2. Now let's substitute the z equals 3 we already had and this new y equals 2 into row 1. In row 1, well, it says x minus y plus 2z equals 9. Well, we know y is 2, we know z is 3, so let's put those in. On the left side, we see a negative 2 plus 6. Well, that's 4. So I have x plus 4 equals 9. Therefore, x is equal to 5. So now we know the x, the y, and the z that solve all three equations. And so our solution, we would write 5, 2, 3. Let's see another example of this. So in example 4, I have 4 equations. Whoops, sorry, pull that down. In example 4, I have 4 equations in 4 variables, w, x, y, and z. We'll do the exact same stuff to work this out. I'll start with my w column. Well, reading the numbers in front of w, I see a 1, 2, 3, and 5. So my first column will have 1, 2, 3, and 5. Looking at the x column, I see negative 3, negative 7, negative 7, and 1. So I'll write those numbers into the second column. In the y column, I see a negative 2, negative 1, negative 3, and 4. So we'll copy those. Going to the z column, we have a 1z, 2z, 3z, and negative 2z. So 1, 2, 3, negative 2. On the right side, negative 3, 1, negative 5, and 18. Okay, so I would like to see a matrix that has, in the first column, 1, 0, 0, 0. We already have the 1, so we need to make these zeros. Imagine now what this means to get these zeros is we're eliminating w. So if I were to say take this w, so this equation 1 and this equation 2, I have a 1w and a 2w. If I could make this a negative 2w and add it to this 2w, then we would eliminate w. So to accomplish that, I'm going to take negative 2 of row 1 and add it to row 2. Now that's going to eliminate w, and I'm going to write that as the new row 2. It's just a new equation in my system. Looking at the first and third equations, I have a 1w and a 3w. I can make 1w into negative 3w and then add it to this 3w to eliminate w. So I'm going to run a negative 3 through the first row and add it to the third row. In a similar way to what we've done so far, I'm going to multiply row 1 by negative 5 and add it to row 4 to eliminate the w in equation 4. The first equation is used to change the second, third, and fourth. And so I'm just going to rewrite the first row of this matrix. By design, the numbers underneath the 1 are zeros. So let's figure out the x, y, z, and the right-hand sides for the second, third, and fourth rows. We'll start with the second. So the new second row is constructed by doing negative 2 of row 1 plus row 2. So let's go to the x column. Negative 2, times negative 3 is 6, minus 7 is negative 1. Going to the y column, negative 2 times negative 2 is 4, minus 1 is 3. Going to the z column, negative 2 times 1 is negative 2, plus 2 is 0. Going to the right side, negative 2 times negative 3 is 6, plus 1 is 7. In other words, by eliminating the w's, I've created the new equation, negative x plus 3y equals 7. Next we see what is the third row. Well, this is constructed by doing negative 3 of row 1 plus row 3. Beginning in the x column, negative 3 times negative 3 is 9, minus 7 is 2. Going to the y column, negative 3 times negative 2 is 6, minus 3 is 3. Going to the z column, negative 3 times 1 is negative 3, plus 3 is 0. On the right side, negative 3 times negative 3 is 9, minus 5 is 4. In other words, by using equations 1 and 3 to eliminate w, I've created this new equation that says 2x plus 3y equals 4. Finally, let's see the new row 4. So I'm doing negative 5 of row 1 plus row 4. Starting in the x column, negative 5 times negative 3 is 15, plus 1 is 16. Negative 5 times negative 2 is 10, plus 4 is 14. Negative 5 times 1 is negative 5, minus 2 is negative 7. On the right side, negative 5 times negative 3 is 15, plus 18 is 33. In other words, by eliminating w in the first and fourth equations, I've created 16x plus 14y minus 7z equals 33. Now that we've got the w column how we want it, let's make the x column how we want it. So it should start with a 1 in the second entry, then zeros below it. To make this a 1, we multiply by negative 1. Currently it is a negative 1, so multiplying by another negative 1 will make it 1. This has no effect on the first, third, and fourth rows. I'm only trying to mess with the second row right now. So I'm just going to rewrite the first, third, and fourth rows. And for the second row, I'm just going to change the signs of all the numbers. After all, that's what happens when we multiply by negative 1. Still have a 0 here, but now positive 1, negative 3, still 0, then negative 7. The idea now is that I'm going to use this 1x to eliminate the x's below it. So if I have a 1x and a 2x, well, I could multiply this 1 by negative 2 and add it to the equation below it. That would give me negative 2x and 2x, which would eliminate the x's. In a similar way, if I look at equations 2 and 4, I have a 1x and a 16x. So if I multiply the second equation by negative 16 and add it to the fourth, I would have negative 16 plus 16, and that would eliminate those x's. And this creates two new equations in the system. Row 1 is not mentioned in this calculation, and so we're just going to rewrite it. Row 2 is only used to change rows 3 and 4, so I'm also going to rewrite row 2. Now let's look at the new row 3. In the first column, we've already got our 1s and 0s, so that's not going to change. By design, the numbers underneath the 1 in the second column should be 0s. So now we're down to finding the remaining 6 numbers. So we go to the y column. This row 3 is constructed by doing negative row 2 plus row 3. So in the y column, negative 2 times negative 3 is 6, plus 3 is 9. In the z column, Negative 2 times 0 is 0, plus 0 is also 0. On the right side, negative 2 times negative 7 is 14, plus 4 is 18. And now we check out the fourth row. Again, starting in the y column, so we're doing negative 16 of row 2 plus row 4. Negative 16 times negative 3 is 48, plus 14 is 62. Going to the z column, negative 16 times 0 is 0, minus 7 is negative 7. On the right side, negative 16 times negative 7 is 112, plus 33 is 145. And so what we've done here, by eliminating x, we've created two new equations that only have y and z. 9y equals 18, 62y minus 7z equals 145. Now the first and second columns are how we want them. So let's make the third column how we want it. We want 1's going down the diagonal, so we wish this 9 to be a 1. Well, I can easily make that happen if I multiply it by 1/9. The first, second, and fourth rows are not part of doing this, so I'm just going to rewrite them. The third row, we're going to multiply everything by 1/9. That doesn't affect any of these zeros. 0 times anything is still 0. 9 times a 9th is 1. That was the whole point. And on the right side, 18 times a 9th is 2. So now I have that 1 in my third column, but I'd like a 0 below it. I always want a 1 in the column and then a 0 and then zeros below it. I've got a 1y here and a 62y here. So if I multiply that third row by negative 62 and add it to the fourth, we would now have negative 62y plus 62y, and those would cancel out. Rows 1 and 2, not mentioned here, so I'm just going to rewrite them. Row 3 is used to change row 4, so I'm just going to rewrite row 3. I'm not meaning to change row 3, I'm meaning to change row 4. Now in row 4, we've already got the zeros in the first two columns, so those are going to remain. The whole point of doing this was to create a 0 here. After all, negative 62 times 1 is negative 62, plus 62 is 0. So really it's just down to finding what's in the z column and what's on the right side. So negative 62 times 0 is 0, minus 7 is negative 7. On the right side, negative 62 times 2 is negative 124, plus 145 is 21. The last thing we need then is a 1 in the last part of the diagonal. I can change negative 7 into 1 by multiplying it by negative 1/7. So I'll take a negative 1/7 through row 4. The first three rows are not mentioned, so we're just going to rewrite them. Multiplying the negative 1/7 by the zeros in row 4 isn't going to affect those, so they're still zeros. Negative 1/7 times negative 7 is 1. That was the whole point. Negative 1/7 of 21 is negative 3. We're finished with the matrix part, and we know that now because we have 1's going down the diagonal and zeros below those 1's. We can conclude in the fourth row that z is negative 3. 1z equals negative 3 is what that equation says. So now I'm going to back substitute into the remaining 3 rows. Row 3 says y equals 2, so that one is complete. We know y, we know z. Now let's go to row 2. Row 2 says that 1x minus 3y equals negative 7, and so that's what I've written here. Now we happen to know that y is 2, so let's put that in there. I've got x minus 3 times 2 equals negative 7. In other words, x minus 6 equals negative 7, and therefore x is negative 1. To conclude then, we put it into row 1, put everything into row 1. Row 1 says 1w minus 3x minus 2y plus 1z equals negative 3. Okay, so I'll write that equation. And now I'll just start putting in everything that I know. I know x is negative 1, I know y is 2, I know z is negative 3. So that's w minus 3 times negative 1 minus 2 times 2 plus negative 3 equals negative 3. Now if we put all these together, I get negative 4. After all, here's a positive 3, negative 3 times negative 1. Here's a negative 3, so those just cancel. So I'm left with the negative 2 times 2, in other words, negative 4. And so w is 1. For the solution, listing them in the order they were presented in the equation in the first place, w, x, y, z, just looking at the originals, well, w is 1, x is negative 1, y is 2, z is negative 3. And so this ordered quadruple is the solution of the system. Going on to the last example, or the last page in this handout. So the procedure we've used so far, getting 1s on the diagonal and 0s below that diagonal, is what's called Gaussian elimination. So one other way that it could be done is we could not only get 0s below the 1s, below the diagonal, but we could also get 0s above the diagonal. This is called Gauss-Jordan elimination. The names aren't really that important. I mean, those are what it happened to be called. So the advantage of doing it this way is you could say, okay, so if I've gotten rid of the 0s above and below the diagonal, then the end matrix will say 1x equals this number, 1y equals this number, 1z equals this number. In other words, there's no need for the substitution because the matrix says the solution directly. So in example 5, so we're going to solve the system from example 3 using Gauss-Jordan elimination. We're going to begin by working with the matrix we obtained in example 3. So I'm just going to remind us what we had at the end of example 3. And you can refer back to page 3 if you like. But the end matrix we had was, first column was 1, 0, 0. Second column was negative 1, 1, 0. And the third column was 2, negative 2/3, 1. The right-hand side said 9, 0, 3. So this is the matrix we ended up with in example 3. So now let's work left to right again, but this time let's instead get 0s above the 1s. So there can't be a 0 above this one because it's already on top. So going to the second column, I would like to make the row 1 entry into a 0. I'm going to use the 1 to create the 0 just like I did creating the 0s below it. I always use the 1 to create my 0s. If I add row 2 plus row 1, I'm saying y minus y, so that would eliminate the y's. Row 2 is being used to change row 1, so it's not going to change. Like, I'm going to rewrite row 2 as it was. Row 3 is not even mentioned here, so I'm going to rewrite row 3. Now let's look what happens to row 1. It's row 2 plus row 1. 0 plus 1 is 1, so that doesn't change. 1 and negative 1 make 0. That was the point there, to make a 0. Negative 2/3 plus 2 would be, what, 4/3. 0 plus 9 is 9. So the last thing we do is we go to the third column and say, let's get zeros above this one. So like to get the first row to be a 0, I could say, let's take, this is a 1z and a 4/3 z. So if I make this a negative 4/3 z by multiplying it by negative 4/3, then I can add it to the first equation and eliminate the z's. Negative 4/3 plus 4/3. In a similar way, to eliminate the z in equation 2, let's multiply this 1z by 2/3 and add it to this z. So I'll take 2/3 of row 3 plus row 2. So all of the progress we've made so far in getting the ones and zeros hasn't changed. Okay, so the first two columns I know. By design, the third column is 0, 0, 1. After all, negative 4/3 times 1 is negative 4/3, plus 4/3 is 0. 2/3 times 1 is 2/3, minus 2/3 is 0. Let's look at what effect this has on the right side. Negative 4/3 times 3 is negative 4, plus 9 is 5. 2/3 times 3 is 2, plus 0 is 2. And so now we see what we found in example 3 at the end. This matrix tells us directly that x equals 5, y equals 2, z equals 3. And that's the end of 8-1.